Okay, so we'll continue from where we stopped last time. And in case you have a question, please interrupt me. And in case if there's any confusion, we even can go back to Dr. Ali. Deal? Okay, let me start sharing my file. Now we're still, we'll talk about the additive mode. We have finished the direct, the immediate. Khalifa, what about the others? Can you hear me very well? What about the others? Is my voice is low? Okay, 1 minute. Okay, is it now? Good? Is it clear now? Okay, thank you. So let's just take a small revision about the additive mode. Last time we issued the based additive mode and the index additive mode, and we went through the direct additive mode, the indirect additive mode. Today we'll just go through the last one, which is the base index. Now, do you remember? Let's focus on the index. What index? An index additive mode. What do I have to use? It's a combination of what? Yeah, I have to use a specific register, which are the SI and DI. Only SI and DI, or do I have to use something else with them? Exactly, I need to use a displacement value or a constant value. So please be careful. There's a difference between if I use SI alone, because if this will be. So if I say, for example, move, okay, let me write this, assume this. What's the additive mode for this? What's the additive mode for this? Yes, please. Yes, indirect. When I add a relative, when I add a displacement, it will be index. So please be careful from this. So what about the base additive mode? The base additive mode. We use which registers? Yes, BX and BB. And with Muhammad, with what? Not only BX and BB. It should be with something else. Yes, please don't forget this, okay? Now the last one that we are going to focus on is called base index. It's a combination of these two additive mode. I can use the base and I can use the index both at the same time. I need one register from the base, either BX or BB, and one register from the index, either SI or DI. Now, do I need a displacement value? Do I need a constant value? It's optional. That's why here is mentioned adding base register and index register and an optional. So in this additive mode, it's optional to add displacement value or a constant value or not. So anytime you see one of the base register with the index register, directly you say it's a base index additive mode. Now here we have this example. I'm moving, I have AH at the destination operand, then I have BX. So this is what? This is a base register. SI, this is index register. So once I see these two together, I know that this is what? A base additive mode. A plus a constant or not. So here the displacement value is just it's just optional. You can add it or not. But once you see one of the base with one of the index, directly you say it's what? You say it's base index. Of course, we are dealing with memory, similar to the index, similar to the base. So we're still dealing with memory. Now, how can I get the address of this? How can I get the address of this? What do I do here? What do I need? How can I get the address here? Now, it's similar to the base and the index. We need this like when we use, like, for example, in the high language, like C++. Like here, I have AI. Remember these? Sometimes we need to get the fifth element, the sixth element of an array, how to move between the elements, for example, in the array. So I have, for example, I'll refer to the address of A to the array, the address of A. This is will be set, for example, in the base. and I have I, this is for the index, and I have 5, which would be the displacement. So think about it that as if we are doing this in the C++, okay, but here in different way. So I'll save the address where that array is saved. I'll just use bx. Then the index, I use just I, like I or j, that's why we call them index. And if I need constant, plus 5, okay, or displacement. So think about this as if we are doing this in C++. That's why we need to, okay, to register one to point to the variable, another one to the index, and we need the constant to get to move between the array elements. Okay, now similar to the previous address mode, if you use here bb, that means you are taking this from the stack segment, otherwise you have to add a prefix. Now here, what is the segment? Is it data segment, uh, stack segment? It's what here? What is the default? Yes, unless we add something else, right? For bx, what about bb? What about bb? If I use this, right, so please be careful from this. Unless you want to change this, you have to add it manually by yourself. You have to do it to add the prefix like this. For example, this will be from the code segment. So be careful from this as well. Right. Now let's study about this. How can I get the address? What do I do with this number? This is equal to what? How can I go to this address? Let's see an example. Like here, I have this instruction, move AH. I have BXSI plus 1, 2, 3, 4. Now, here we are where? In the data segment or the code segment based on the instruction values? Here, or the register values. I'm in the code segment or the data segment? Hint, think again. Think again, hint. Look to the value of CS. Look to the value of DS, yeah, hint. Where am I exactly? This is which part of the memory? Code or data? Code segment, yes. Okay, hint, you can miss. What are this column? Remember, what are this column? What is this column? What do I have here in this column? What are these values? Remember, we translate the assembler will translate each instruction and to a right machine code, to the object codes. So this is the object codes. How many bytes I have? Exactly, yes, yes. من حصة. Why two? Think about it. Why two? Here, how many I have? Look, how many bytes is taken from the code segment? How many bytes? Again, how many bytes I'm taking from the code segment for this instruction only? 4. Who wrote 2? حصة wrote 2. Why 2 حصة? منتلة also. Why 2? Yes, thank you. Okay. So yes, it's taking 4, and remember, is if the instruction part of it, as Dr. El-Moursy said before, part of it's constant, this part will be shown as the object code here. Like here, I'm using 1, 2, 3, 4 as constant. It's showing here part of my object codes, right? We studied this last time. So we are fetching, and we know we did the translation of the instruction. Now, what is the next step? I have to point where now? Do I go to the data segment or what? The data segment should be pointed where? To which part based on this? So I fetch the instruction, right? Now I need to go where? To execute the instruction. What is the next step? Yes, ya Hajar, which means what? Not, I need to point where, Ragad, before going to BX? No, before going to BX and SI, no, where do I point now? I need to go to the data segment, right? I need to refer to the data segment. Now data segment is 02, which means 0200. I need to refer to this part here, right? I need to go to the data segment because by default, once I use BX, I need to point to the data segment, right? Type. Now, how do I know the physical? How do I start executing this instruction? How do I do this? I need to get the physical address of this. This means what? This means what? How can I get the offset? It's bx. You add bx, whatever in bx, plus si plus 1, 2, 3, 4. Can you do this for me? So, to know this content exists where exactly, I have to get the address of this. So what you do, you get what's in bx, you add it to si. Okay, remember this is base index. I have two registers, one from the base, one from the index, plus an optional, because here I have a constant. I have a displacement value. So what you do, you add all of them together. Okay, so we got the address, and then the value of this, please, I need to take it from the data segment. Why data segment? Because remember, whenever I use bx, by default, if there is no prefix, I just directly go to the data segment, unless there is something else. Okay, can you calculate this for me? It will be equal to what as a physical address? So I just know from where do I get the memory. So Maha said 000 plus 0200 plus 0123. So yes, yes, yes. So you have added this, right? Bx is 100. Bx is 100 because in Bx I have 100, right? In Si I have 200. In Si I have 200. So if we add these, from where I got this number from the register in Bx, I have 100. I just took it from here. In Si, I have 200. I take it from the register Si, from the index register value, then plus the constant. If you add this 1000 plus 2000, 3000, this will be what? I don't have space here. I'll just write it here. 4234, right? Right? Yes, Tamara. So now I want to get the physical address. Yes, the physical address. DS, this number. How can this? It will be equal to what? Remember, we add this and we need to add a zero. So it's 02. It's 02. The physical address, I'm just computing now the physical address, plus 4234. So this will be 06234, which will point here. So this is the physical address for the content of this. Got it? How did I calculate? Just bx plus si plus the constant. Then I got the offset. Now I just get the physical address. I just add a 0 to the ds and just normal calculation for the physical address. It will be coming here. So I am here. How many bytes now I'm going to take? So I'm moving. This is my source, which is here. Okay, I'm here in this point. How many bytes I'm going to take? Yes, 1 byte. Why 1 byte? Yes, hint. Because remember, the destination is 1 byte. If the destination is 1 byte, I'll take only 1 byte. Now it's the time for execution. Now, what's the value here? Which register will be affected? Which register? What I'm going to change from here, or here, or here, or here, or here. Now I just execute the function. Yes. AH, it will be have the value. What's the value of AH? It will be equal to what AH? لحظة عمر. عمر again. Yes, Hind. Yes, Muhammad. Yeah, remember I'm pointing here, right? I'm pointing here. Why do I go here? I'll just take the byte here. Why do I shift here? Omar. So based on our calculation, it should be pointed to this. So just take that byte and save it in AH. Why do I go down? So I have calculate the physical is 06234. So I'll come here to that physical address. Could be only 1 byte. I'll just take 1 byte, and that byte should be saved in AH. So in AH, I should save BE. So please, this will be saved in AH. Are you convinced? Sheikha said ED, Omar said ED. Omar, are you convinced? It is not high byte. Ragad, no. Uh, yeah, I know you are confused about this. Now, no, it depends. You are pointing me. It does not, but if I'm high, I'll take the next one. No, that does not mean this. This means where I'm pointed. Okay, I'm pointed to this, right, Ragad? I am here. So this is my physical address for this, for the source, right? So I'll go there, take the content, take only 1 byte, and save it where? Save it in AH. Okay? Uh, A high here does not mean go to the next higher byte. No. Or to the next position of the address. No. I'm pointing here. I'll take here to my destination. That's it. Got it? Please don't confuse between this, between the Little Indian order. تمام؟ طيب, let's Hind, she's asking if this is AX, if this, yes, thank you, Hind. If this is AX, what will be AX value? Let me write here. AX, it will be equal to what? Yes, you are right. What is AX? If I change here the destination from AH to AX, what's the value of AX? Since the destination 2 bytes, I'll take 2 bytes. Let me see. EDBE. Yes, EDBE. Yes, EDBE. You are right, Olga. Yes. Got it? Another thing before I proceed, I want to be sure. Assume I wrote this instruction in this format. Okay? Remove this. What's the difference? Any difference? Do I have any difference? No. Yes. If it's outside or inside, there is no difference, guys. Yes. So this is regarding the base index. Once you see base register with index register, either with a constant or not, you consider this a base index addressing mode. Any question? Type. Now this is, we did it, we already, and okay, now this is a good example here. Try to not look to the solution and do it by your hand. Let me put some boxes and just do it together. I'll just add boxes. Okay. So okay, I don't care about this. It's okay. Now here I have a data segment. I start from 0040. This is the offset. I have a label, right, called TBL, defined byte. Then I list some bytes here, 98765. Okay. Now they move the segment to AX. In the segment, I have zeros. In DS, I initialize DS with zeros. So the data segment is initialized with offset 00, right? Now what I need, move BX plus 1 to L. What is the addressing mode here? What is the addressing mode? Before we execute, what is the addressing mode here? I'm using a base register, right? Base register and a constant. Yes, yes, exactly. Now, if I remove this one, what will be? If I remove the plus one, it will be what? If I remove the plus one, it will be what? Yes, exactly, Lubna. Yes, exactly. So be careful. Now, how do I calculate the physical address? Give me the physical address. Plus whatever in BX. In BX, I have 0040, which is already assumed here. So 0040 plus 1, of course, I'm taking this from data segment. Remember, BX by default, that's what pointed to the data segment. So the physical address 0041. So I'll go to 0041, which is this one, 08. So do I copy 1 byte or 2 bytes? Yes, hand, yes. Yeah, what about the others? I have maybe 10, 11 are with me and the rest are watching. So exactly, only 1 byte because, yes, exactly. Only 1 byte because the destination is 1 byte. So what is an AL? I'll have what? AL equal? Equal which one? 08, yes. sure that you did it right. Yes. Now the same. What about this? Now please focus on this. This is a little bit different. Now I have move AL SI plus TBL. What is this? What's the address mode? What is TBL? Remember, TBL is a label. I use it here to declare what? To declare these variables. Do we consider this? How the assembler will deal with this one? The assembler will deal with these labels as a constant. They will convert this to the constant. It's equal to what? Okay, so let me see if you have. Yes, Abdulrahman. Yes, Abdulrahman, it's the data segment. طبعا you add 0. Got it, يا Abdulrahman? Go here. If you come here, look here, يا Abdulrahman. In data segment, I have 4 zeros. And when you calculate the physical address, we add extra 1. We add this 0. So data segment plus, yeah, that's 0. Right? Because BX by default, I'm dealing with data segment. Now, what about here? Now, notice here, do I consider this indirect or do I consider this index? Now, as I said, the assembler will convert these labels to constant. They will consider them like as if we are using a constant value. So we'll just do the translation. What is BL? TBL is in the data segment. So it will give you the offset of this one. So what's the offset of this one? Look here. It's what? Started at org 0040, started at the offset 0040. So the assembler will translate this label to its offset. Okay, it's belong to where? So this is 20040. Now this is the TBL. What is 002? It's the SI. SI plus TBL. SI I have in SI I have 002. Then I have what? Data segment. Okay, because SI by default also data segment. Again, when you see this, consider this as a constant. So when I ask you now, what is the additive mode, you have to tell me it's index because I have one of the index register plus a constant. We call it index additive mode. Got it? Yes, Tamara, yes. Yes. So please, anytime you see the label, go to that label, check what's the offset and add it here. It's not register or something. The assembler will understand this label as a constant. تمام. So now if I calculate the physical address, data segment with plus 0, then plus SI plus TBL. TBL pointed to 00. Remember, I got the TBL because from the org, in the org is 0040. It's pointed to this offset. That's why I take it. Then I got the physical address, it's pointed. So what is now AL and how many bytes? Since the destination is only 1 byte, I'll take only 1 byte, which is pointed to 0042, which is equal to 7. Easy, صح? Muhammad, error. Yeah, tell me, Muhammad. What if someone names his variable the same as the register? Like what, AX? AX, BX? Remember, Muhammad, you are a programmer, right? And you have to understand your your syntax and what you are using, right, before you do the programming. So if you call yourself AX, I did not even try this in Visual if I tried to declare a variable, but I think it will show you an error because it's already reserved in the software. However, you can try it. You can just make. Okay, Muhammad? Makes sense. Yes. Damn. So now last one. Once I see a base, what's the address signal here directly? Even if I have constant or I don't have constant, what is the addressing mode here? Base index. Okay, so what I do here is the same. I'll just get the value. Of course, this is still data segment. That's why I have Ya Abdurrahman zeros. And since I'm calculating the physical address, I'm going to add another 0. Then the value of what? Of BX, then the value of SI, then the constant. Add them all them together. You are going to point to 0043, which is what is it's here. I'm pointing here. Now, since the destination is only 1 byte, I'll just take 1 byte and AL it will be 6. I think it's clear for you. Yes. So this is what everything has relation with the additive mode. Go through them again, please. Try them even in Visual Studio. Try them practically. This will give you more experience and will improve your skills in programming. Okay. Now, again, as a revision here, remember the direct, we use a constant value like 1, 2, 3, and we did this before with any segment, it's okay. In the indirect, okay, I need to save my address in one of the register. I cannot use it directly. I need to save the address first in the register, then I can use it. And this is the format for the indirect. Then I have the base. In the base, it's like a combination between the embedded, as we said, because we need to use a displacement value of 8-bit or 16-bit, but it's a must to use a base register, either AX and BB. And please be careful for the default segments, okay? Because once I use BB, this means I'm taking this from the stack segment unless you change this to DS or CS, unless you add a prefix. Now the index is the same as the base with but exactly the same but with different registers. Here I'm using SI and DI, and it's not optional. Here the displacement is a must. You have to add a constant value with 8-bit or 16-bit. Yes, and the base index, I need to use both, one from the base register, one from the index, plus a constant is optional. You want to add, you can add, you don't want to add, it's okay. So this is for the addressing modes, and here he's giving you that be careful, don't use, we cannot use the instruction to move between memory to memory, right? Can I write, can we do this? Can I do this, for example, move, can I do this? No, we cannot move memory. So here you have all the option. You have memory accumulator, AX memory accumulator, register to register. Yes, we can do this. Memory register, yes. Embedded a constant value with a register, constant value as a source to a memory, yes. Register to a SIG register, and be careful, should be 16-bit, because when you use the instruction, both operands should be matching in the size. So for example, I cannot move AXAL, right? I cannot do this because both are different size. So when you do the instruction of move, you have to take care of the size, you have to take care of the type of the operands, the source and the destination. And you cannot move, like, can I do this? Another one. Move. Can I do this? Sorry. Like, can I do this segment to segment? Do I have this? Exactly, I cannot do this. And if you notice in the previous example, they move it to one. Let me, where is that example? Yeah, they move CS first to a register, then from register to DS. They do it in 2 steps because they cannot segment to segment. They cannot do it directly. So please be careful from these mistakes and these errors. Okay, so this is all the option where you can use move, and it will apply to most of the instruction that we are going to deal with later. Even for example, if we are dealing with add sub, we cannot add two memories. Okay, now here we already talked about this. When we write the assembly file, first we start writing the assembly instruction in a text file, right? Text editor, and we call this .asm, and I believe you did this step before in the Visual Studio. And once you finish, okay, once you finish, of course, what do I have here? Here, let's listing you that editor file includes what? It has instructions, some variable labels, like sometimes I can declare any variable I need and give it a size, some directives. um, Directives means what? Directive mean, like we talked about the size before, right? Remember the define byte? Okay, did you study this in the theory? The sizes, define word. I believe you studied. Yeah, all these we consider them as directive, like org. We call them directives. So part of my assembly file with .asm, I'm going to have some directive in this file. Okay, instructions, some labels, symbolic names for the instruction. What do I mean by symbolic name for the instruction? Like move. Okay, so this is the name of the instruction, like add, mul, sub, increment. All these are symbolic name for the instruction. The assembler will translate these names to the object codes, right? So when I write move, for example, AX, the microprocessor will not understand move, the word move. I need to translate this to the object codes. So this is the job of the assembler, do the translation. Then after you do this, once you compile your file, and there will be two files generated, the listing file and the object file. Now we already studied this, the listing file also in the lab. Listing file include, and I'll show you now example, we'll show you all the details, we'll show you the object codes for each instruction, how many bytes each instruction is taking, how the variables are declared in the data segment, what are the relative addresses there. All these information will be part of the listing file, the symboling names, the labels. Even if you did some errors while you are writing your code, these errors and warning will be shown in the listing files. Yes, Hind, thank you, Hind. Thank you. You are listening. Yes, yes, Maha, please go ahead. No, no, yeah. She's asking Maha a good question. She said, will I get the same address for these two instruction? Move ALBX plus one. Uh, oh, what do you think, Maha? Give me yours. Let's take the first one. Uh, I'll copy this instruction, okay, Maha, and I'll ask the students where I'm going to point here. Where I'm going to point. To execute this instruction, where do I have to go? Give me the physical address. The physical will be equal to what? Yes, exactly, Abdi. Aziz. Directly, I'll go Yamaha to the data segment, right? And add a zero, then plus what's I have in bx plus one. Tamam Yamaha for this instruction. So I'm pointing to the segment. But what about the next one? Look to the next instruction she wrote. She wrote this. What is the physical address here? Do I go to data segment? No. Since I have added a prefix, I'll point to code segment. So you go to the code segment, take the content and save it in AL. So different segment. Yes. Got it, Yamaha? Now for BB, for example, be careful. For BB by default, yes, yes, Maha. Yes, even. Yes, Yamaha, even. So I have a question. What if I was BB plus SI? BB plus SI. Tamara, you are asking about which one, Tamara? Uh, stack, yeah, Tamara. Yeah, BB plus I. Let me be sure from Dr. Ali about, but I believe it will go to the stack segment. Let me just be sure from Muhammad. Muhammad, let me just be sure, but I believe that it will go to the stack segment. Just, I don't know if Dr. Ali here. Yeah. Let me just be sure from this point, guys. I believe it will go to the stack segment BB plus SI Muhammad. Okay, I believe it will go because it will look directly to the first address, and once the first is BB, it will go directly to the stack segment. Yes, I believe this. I remember this. This is how I studied before. But I'll just ask Dr. Ali this question, and I'll ask him if he will be with you on Thursday to verify this one. But if we are talking about separate BB like that, this is directly to the stack segment. If it's BX, this will be data segment. If it's CS BX, I'm sure from this will go pointed to code segment. Okay. About the BB plus, for example, SI, I believe it will go to, but I'm not sure from this. I have either to try it or ask Dr. Ali about this. But it will just point to the first address, check it, and point to the segment. But let me be sure from this. Clear, Maha? That's why if you notice Dr. Ali in each slide he's trying to explain this. That be careful is pointed to which segment. تمام؟ Else. Okay, so this is then it generates for me. Once you build your code, you'll have the object file. This is the file that the processor understands. It's the binary file. The processor will understand this file and will use this file. Now sometimes we can, over the linker will help us to generate a file with executable. Now usually we did this even before. If you notice this in like in C++, the extension of the file .exe, and you can run it anytime, especially when we have like user interface, when we have like inputs, you have to add input. Remember the black screen? The black screen, or think about it like when you run any software, what's the file executable? It's like .exe. Okay, so sometimes if you need to generate the executable file, okay, with the extension .exe, it can be generated, and anytime you can run it and view the result in the black window. Do you remember this? We did this before in the C++. We have the black, and every time we just open the executable file and we just add our inputs, then we check the output directly. So this is the steps we generate. For example, we start by the editor, we write our instruction, then we have the listing that include all the information, object file that is understandable by the processor, and I can have the executable file. Now, we already talked about org. Org will initiate, do I start from which offset? I can control this in my program. I can just say org and directly I will just start. I can do this in the data segment, and I can do it many times. I can have more than one org, and we consider org as directive. As I said, in our code, we have some direct, like define byte, org, define work. All this, we consider them directive, so that already this is understandable and used in the code. Okay, you studied org before, right, in the theory, or it's your first time? Yes, yes, Hind, yes, yes, in the 8086 first time. Okay, so let me show you this again. This example here. Okay, yes, Max, yeah. Listen to here. Here, if you look here, when I start, like I want TBL, I want the TBL or this data variable to be located in a specific offset. How can I control this? Originate will help me to do this. So how do I, for example, okay, position TBL exactly at offset 0040 by using org? Okay, if I did not use org, assume I don't have org, okay, you don't know what is TBL. Can I know where is TBL exactly where? I don't know. But if I want to control the position, it start from which offset exactly, I'm going to use org. So this means that all the data, okay, TBL will be now pointed to the offset 0040. So where is the offset 0040? It's this one here. And as hinted in 8086, we cannot exceed 2 bytes. So that's why this is TBL. It's pointed to this as 04. Yeah, this is the offset. So anytime you want to control, okay, the offset, it starts from which offset, just directly you use org. And we use it a lot. Sometimes I'll ask to define a data variable that start at offset 0042 or 0043 or 0300, whatever. So you have to use org. Once I give you this condition, start at this, position your data labels at that, you have to use org. And we consider org as a directive. Clear? It has a maximum because if you use more, if you add it, maybe you will exceed the limits. So don't use more. Okay, so don't use more. Maybe you will exceed the limit. When it add the physical address, it will exceed the limit, exit the limit. So just make it 2 bytes, not more than this. Okay, Abdulrahman, I'll talk about this. in the lab? Why do you make it to 2 bytes? There is limitation. There is limitation because remember we divide the memory to segments. Yeah, even if you try this in Visual Studio, there is limitation. You cannot exceed this. تمام? Yeah, don't exceed the 2 bytes here. Okay. Now, still, if you have more question, you need more details, okay? Once Dr. Ali, you can ask him about these details. So don't worry. Okay, now EQ, you already did this also in the lab. Whenever we declare this is another directive, we use it. Depends, sometimes we use it. Now, remember the const in C++? In C++, we use const. This is whenever I need to use a constant value for any reason, then I want to get the result, use it temporarily. Okay, this is the same thing EQU, but in assembly. Now the question, does this directive, does this type give me reserve any memory location from memory? No, it does not reserve any memory location. Okay, it's just a constant. So the assembler, once we see that label, see, I'm not using here define byte, I'm not using define word, I'm just giving the type EQU, which means this is constant value. It will not reserve any memory. So during the execution, okay, the assembler will do what? The assembler will do what? Before the execution, the assembler will translate this to the constant. Once you see the label, like here I give it a label name len. I can give it, for example, Maha. So once the assembler will see Maha, just translate this to 32, translate this to a constant value. So sometimes we need it, sometimes we don't need it, depend on the question. However, please be sure that this will not reserve anything from the data segment. You will not do. It's just what it will translate the label name to a constant value. So sometimes because we want to make our software too general and we to be a professional code and we don't want to use any constant beside the code. So just come here, for example, I don't want to use 32 now, I want to use 45, I just add 45. So now len will be translated to 45 as constant. So this is EQ. You can even try it in Visual Studio and see how it's working. So instead of using constant, I can just give it a label. I can give a label to my constant. So this is another one. Here, directive for the sizes. Here it's showing you that we have define byte, define word. And for example, here I have a string. How many bytes I have here? How many bytes I'm reserving from the memory? Yes, for each letter, yeah, each letter will reserve 1 byte in sequence in order. I'll go from H, then E, then L, another L, then O. And this will be translated to what? Please be careful. This will be translated to Ascii code. So H, what is the ASCII code of H? It will be, you will see it in the memory. What is the ASCII code of A? It will be, you will see it in the memory. What is the ASCII code of L? Of course, you have the same, yeah. So be careful of this because these are characters and we refer to them as ASCII code. So this is, yeah, these are defined by define word. All this we consider them as directives. Sometimes I can add the labels. I can add labels to my instructions. So here I have, for example, move AX offset and I add a label here. It's similar when we use go to or return to in C++. So sometimes, yes, I need to add labels even in the code segment, and we will do this inshallah later. Yeah, define word is a directive that give me 2 bytes. It's reserved for me a word size, which means 2 bytes. That's why you cannot exceed here. I cannot add any other elements here. Maximum is 2 bytes. Anytime I want to add a variable, like here I'm adding a variable in the data segment msg size of 2 bytes, and here maximum I can have 2 bytes. I cannot exceed because I need to follow the site that I have referred. So define byte, define word, all these are directive, and of course define word, it will reserve 2 bytes from the data segment. And still labels. Okay, now here this is used in not NASM assembler, this is used in another assembler called NASM. Here I can reserve a memory, and memory here when I write RESB, this is a directive, this will reserve for me a number of bytes, but this will be uninitialized. Okay, there is no content there, I'm just reserving them, but they are not initialized. Okay, why do I need this? Why do you think I need just a reserve a memory location without saving anything there, without initialization? Why do I need this in programming? Why do we need to do this? Later used by what? Okay, for later used by what? Exactly. For example, if I array of elements, okay, and I ask you please uh, add them and save your result in a location. Okay, so how do I do this? If I ask you this, how do I do this? So I have, for example, array, assume the array offset 300, okay, hex. So I'll just say my array, I'll call it array. It's just an example. Array, I have defined byte, then I'm listing some element here, 2, 3, 4, I'm listing some element. Now just then I ask you please add these elements, add them and save the result in an address pointed to offset, for example 400 hex. Okay, so I just here I control the offset by the org directive, then I just say sum, then I can say this is the label RESP. I can just reserve some byte here. Okay, like here I'm reserving 5 bytes, here I'm reserving 4 bytes. It's up to you how many bytes you want to reserve for you. So later on I'm just I'll go there directly and save my result there. Yeah, sometimes we need to do this. Now in the Visual Studio we did this before, and we can do it in this format. If I know the size, if I know the size of my output later, I can give it a size and I can add a question mark. So this also will help me to reserve memory. Got it? There's a gap between you and me. That's clear? Reservation. I'm just reserving without using. There is nothing initialized. Okay, so RESP, it will be reserved as byte, number of bytes in the memory. Okay, just for reservation, nothing else. Maybe yes, Muhammad, yes, we did this in the lab, yes. Just to use it temporarily, then we'll not use it. Like when we swap, yes, we can use it, yes. Now this is the RESP, another one is the RESW. This is the same thing, okay, but the different size. I'm reserving word size. So if I write 5, how many words I'm saving? I'm reserving, sorry, 5 words. And this means how many bytes? If I'm reserving 5 words from the memory to my program, how many bytes in the memory? Exactly. So be careful. So I have ERESP reserve bytes or RESPW reserve words. So these two, okay, in the Visual Studio, in the MASM, we don't use them. These are undeclared, but these are used in NASM assembler, another assembler. Now, last thing, yeah. Now, we know that in the simply we can use ASCII code, we can use decimal value, we can use binary base, we can use many bases, right? Binary, decimal, hexadecimal, we can use the characters which are ASCII. All this the assembler will do the translation by itself. Okay, so yes, you can use any format. It is used in, yes, MASM assembler does not understand. Yes, Hind. You use it, of course. Otherwise, why Dr. Ali mentioned it? Yes. But if you try it your hand in the Visual Studio, it will not work because we are using Massim. Yeah, this is different issues. Yani, every time we deal with any software, like you have to understand this is used what. Can I use this one here? Did this assembler understand this or does not understand this, and so on, right? This is our job. Like for me, how did I know this? I just went to Visual Studio and tried it, and I searched on it on Google. I found this is for Nassim assembler. Yes, yeah, of course. The assembler and the microprocessor architecture, all these, of course. Remember when we talk about the object codes, we said even it depends on the microprocessor. So if you have instruction and all this, we have to go back. Object codes, we have to go to the microprocessor itself. And when I execute the instruction, yeah, I have to know the assembler. These directives are declared and reserved for this assembler or not. Okay, so the RESP is not with the Massim assembler. Even you can try it by yourself. Okay, now as I said, sometimes we use the labels, and once we use the labels will be as a constant. Please be careful. Like before we use len, we use maha. Once the assembler will see this, we'll just translate this to a constant value. So we did this even if you notice this in the base additive mode, we did bx plus tbl. Yes, once I see tbl is a label, it will be converted to constant. So all these conversion, um, different types of bases, convert the label to a constant value. All this can be done and understandable by the translation done by the assembler itself. Okay, even before giving the machine code object codes. Yes. So sometimes we say len plus 2, it will just add, it will just translate len to a constant value, and it will add 2 to it. We did this now. Okay, so labels will be just translated. Here we have like example of the assembly file, and this is the syntax that we use in the lab exactly. It's divided to segments. In the data segment, I may have data variables. I can declare as many as I want. I can have more than one org to control they initiated from which offset. Then I have the instruction in the code segments, and I can use different addressing modes, right? So this is already, we did this even in the lab. This is our editor where we write all the things that we need, variables, instructions. And what I want to focus on is the listing file. In the listing file, we have many columns. The first columns is the program counter. It shows me the line numbers, okay, how many lines I have. Okay, it shows me all the syntax lines like .386, .model flat, .sd call. All this is part of the syntax of the software, and they have a meaning for this. Then if you notice here, what's the starting offset for the data segment? What is the starting offset for the code segment? Let me enlarge this. Yes, they will start by zeros. Yes. So every time by default they start by zeros. Now if you look here, what are these? What is this column here? Like I have a message, a data label has, okay, message defined byte, and I'm listing characters with some value. Byte 10, which is A in hexadecimal, byte 13, which is, okay, D in hexadecimal. This is a test programming, some characters. All these are saved where in the memory. Now what do you think? What is 0A, 0D? And why do I have here 0010? Why did I start from 0010? We said that data segment start from 0. Why I moved to 0010? Why I jumped? Because of what? Exactly, because of the org. The org will send me to 0010. Then I start the content, right? 0A. What are these? 0A, DD. Then I have 54 or 0D, sorry. 0D here. 0A, 0D, 54. What are this? What is 0A? 0A is the 10 here, the value is here. So 10 in hexadecimal it's A. 13 in hexadecimal is 0D. Then what is 54? 54 is the Ascii code for the T capital. 68 is the Ascii code for H small. Then I have 69 is the Ascii code for I, and so on in order. So all these are what? Okay, the Ascii code of the letter, and we'll consider them. Okay, so be careful from this. You can go to the Ascii table and compare these letters, the Ascii, with the letters itself. Now, once I finish, okay, that the segment ends. Of course, it depends how many bytes. So if you do difference between 2A minus 10 and hexadecimal, you will find the number of elements here, the number of bytes here. Then we move to the code segment. It start, okay, start, or we say it main. Now it starts from offset 0 and it will go to each instruction. So this is the first instruction. Move, for example, AX data sig. Now here, how many bytes I'm taking for this? How many bytes? I have B8 0000. It's 3 bytes. That's why the next instruction, and this is referred to IB work. Remember the instruction pointer? Okay, so 003 is the next instruction. Why it started from 3? Because byte 0 is 1 to B8, byte 1 for 00, byte 2 for 00. So 3 bytes for this. That's why I'm starting here 3. For the next instruction, 8E D8, I have 2 bytes. So if I ask you when it will start, or what is the relative address for the next instruction, you are going to say it's at 5 because it's taking 2 bytes. Now this is okay. Now notice here, all of them I'm using move instruction, but I have different object codes in the code segment. I have B8000 for this move. I have another move, but different instruction, different number of bytes. Again, this is depend on the architecture of the microprocessor. Okay, move with, for example, memory, move with 1 byte register, move, for example, if I'm using move with 2 byte register, all this will give me different object codes. So does not mean same instruction, same object code. Depends on the address modes too. Minimum, yes, Muhammad. Minimum it will take 2, but maybe more. Now let's see. Let's take this an example. Look to this. Look to this here. Here I'm using 2 bytes, right? But it's taking 3 bytes. Okay, as if it's pointed to BA to the move instruction, and 2 bytes, and C000F is the constant value. Remember, when it's a constant, it will show the constant value part of the object code. Okay, like here I'm using AX with the memory, it show you the same. Here I have the constant value and A1. Now here it's A1 because I'm dealing with memory. Here it's B8, I'm dealing with the register. So it's different. Okay, here I have, for example, AX with the memory. Here it's showing me 2 bytes only. Here I have DI with offset. It's showing me 1, 2, 3 bytes. So it depends on this. Got it? Different size, different notation, different addressing mode, different size. All this will affect the object codes, of course. Okay, so do you understand the listing file? Instruction is object code. It's showing me how many bytes. Any question about the listing file? Do you have any question? So even here we have more instruction, you can check them. And to know this even, and to try this, go to Visual Studio, type the instruction, then see the listing file, type another instruction and see the listing file, and so on. Of course, here the format is different in the Visual Studio. See some different, we talk about this in the lab. Slide 64. Slide 64. We don't have slides. Line 64. This is which line? Which line? In which line do you mean? Abdulaziz, what last line means in slide 46? allows for quickly changing sizes of arrays or lists. This is what you mean? This one, Abdulaziz? Yes. Now, here, if you notice here, for EQ, do I have any size? There is a size for this? I can use any size I want. So, for example, I write a code. In this code, I need 45. Okay. So let me do this here. Okay. Let me do simple example. Move, for example, AL, for example, len, something like that. Move AX len. So see, I'm using this constant in many instruction. Okay, Abdulaziz, I'm using it in many instruction. So the point of this, instead of every time, okay, I use 45, I use a label. Now why? Why? I wrote now the code with the len 45. Now I have changed my mind. Okay, I want to use another constant. And instead of coming here, okay, and change 45 to another, I'll just directly go here and change it only one time. I'll just change this to, for example, 200. So see, different size. I didn't care about the size, okay? And it's very fast. I only change it from here. I didn't change it from here and here. Got my point? So it will simplify my life and it will make my code professional. When I change anything, I change only the input. I don't change the instructions. So for example, if I ask you to add, for example, something to a fixed value, so you did add, then I change this value to something else. So you come here and you change it from here only one time, not on all your instructions. So yeah, that will simplify and make your programming is faster without taking care of the size, of course, because there is no size for the constant. It's just a constant value. Got my point? Okay. So we finished from this. I just want to go very far. Dr. Ali asked me to go to add, but I don't think I have time to finish. Now here we'll start talking about more instructions, okay? In this chapter, we'll start talking about the instruction. Till now we have studied only the move instruction. Now we'll deal with more instruction. Like we have something called data transfer instruction. This is when you move content from one place to another place, okay? So we call it data transfer instruction. Now we'll focus on arithmetic instruction, like what arithmetic? Add, sub, mul, divide, negate, increment, decrement. All these we consider them as arithmetic instruction. We have logic instruction like AND or XOR, shift instruction, shift to the right, shift to the left, rotate, also rotate to the right, rotate to the left. So we are going to study all these instruction and we'll go through them one by one. For data transfer, we already did this since we use move, because in move we transfer content from another content. Hind, you can send email to Dr. Ali. I'm not sure from this. Okay. So what are the data transfer instructions that we are going to focus? We have studied move instruction, and we have the exchange, and this is really nice, the exchange instruction. And we have something called translate byte instruction called extract, and loading effective address, load data segment, load extra segment instruction. However, I'm not going to focus on all this now. I'm going to talk only the first two, the move and the exchange. If you want to go through the others, you can go through them later by yourself. But these two, the instruction that Dr. Ali wants you to understand now, the move and the exchange. Now, as we said, when we deal with any instruction, we have to understand the syntax. How do I use this instruction? What are the inputs of this instruction? What are the outputs? The output, for example, when I got the result, it's saved where? So where is the source? Where is the destination? Do I use it with register memory or not? So I have to understand all these things. I have to try it with myself. So we already talked about the move, and we refer what type of sources and what type of destination. And we said we cannot use memory to memory. We cannot use segment to segment. Now, yes, this here example, I can use a constant, okay? And here it's showing you that, of course, I can use a constant when I'm dealing with data registers like DXPX. So he's asking you where we cannot use, like for example, segment to segment, memory to memory, and constant to segment. So all these are not part of the syntax, cannot be used with the transfer instruction like move. So I cannot even use move with data segment, okay, or code segment or stack segment. No, I cannot use constant or embedded value with this. So this is forbidden. It's error, okay? We cannot do this. We cannot use DS, CS. This is another forbidden. I cannot use move with what give me, like I say, yeah, DI, for example, VX, memory to memory. I cannot do this. So these are the cases that we cannot use them in that format. We cannot use the instruction. Memory to memory, okay? Constant to segment and segment to segment. So please be careful from this. Another thing you have to be careful when I deal with memory, for example, as I said, we have to take care of the size. So I cannot, for example, say move BL DX. Can I do this? No, because the size of the source does not match with the size of the destination. Both, they should be same size. If I use here 2 bytes, here I need to use 2 bytes, or the opposite. If I want to use 1 byte with 1 byte, like DL, yes, I can use it with DL. I can use it with DH, yes. So these are the things that you have to be careful when you use move. The size, type of the source, and the appearance. I should not make memory, segment, or constant to segment. Is that clear? Got the point? Okay. Here showing you example, like here how we declare C, for example. Again, I'm focusing on the org. Org will let me, give me the chance to control from which offset do I start. So here I'm starting from offset 1000 hex. I'm declaring some defined word, and I'm doing what here? I'm just doing reservation. I just have reserved some places for my sum, which means later on in my code, I will use that address. I will use this position to save my content in. Now here I have another label and the size of this defined byte, and I give it a value 20 hex. Okay, so here just an example how to use the move instruction. Okay, so I'm just loading the data segment to AX. Here make AX. Okay, initialize DS with the AX. I'm pointing to the DS. Here memory, I'm just going to the memory, take the content and save it in X. Just examples. Okay, so here I have the source to memory to CX. So everything is fine except these 3 cases: memory to memory, segment to segment, constant to segment with move instruction. Now later, another very nice and easy one, it will simplify the exchange. Now in the lab, I ask you many times to swap the content of this register, swap the content between AX and DX, between AL and BL. And what you did, you use move. And to run this, you use 3 instructions instead of 1. Remember this? In the lab. And instead of using 1 instruction, you use 3 instructions, right? Yes. Here I can. Yeah, just yes. Hint. What's the wrong? What's the wrong? It's empty. خليها empty. This is just an example, yeah, hint. That you can move memory to register. It's okay. I can use move. Okay. Yeah, even it's empty. It's okay. Right. Now here. Yeah, this is the exchange. In exchange, it will just exchange the content. So if I say exchange sum with AX, see, I can use memory with the register. It's okay. So what will be the content of AX will be saved in the sum, and the content in sum will be saved in X. I'm just swapping, okay, between these 2 content. So whatever in AX will be saved in sum, and whatever what's in sum will be saved in AX. So this is the point of exchange, exchanging the content of 2 operands, either source with the memory or memory. I can use this with the registers. That's okay. Source mem is 1/3 because sum not allocated yet. Source sim. Let me go to source sim. No. Good question. No. Now in sum, how many bytes for sum? I'm taking 2 bytes. So here I have 100 offset 1 and 1002. Right? I'll take 2 bytes for sum. Who asked me? Tamara. Yes, Tamara. I have 2 bytes for sum. 1001 and 1002. تمام. So this will be even. No, I reserved for memory. It's taking, but there is nothing there. Okay, there is nothing there in these 2 bytes. That's why I put a question mark. There is nothing, but they are there. I'm reserving them. So source mem will start from 1003. Got it? Okay, Tamara. Okay. Now we finish from this exchange. I feel it's just you swapping between the content of the source and the destination appearance. Okay, the Artemic instruction. We have addition, we have subtraction, we have multiplication and division. For addition, what are the additions? What are the addition instruction that we are going? We are going to use add, and I can use this with 1 byte or 2 byte. Remember the 8086 you use 8-bit or 16-bit. I can use AL or AX. I have add with carry. We know what's the carry, right? Sometimes when we add, we may have carry, right? We have a carry. So sometimes, yeah, for the I need to add with a carry, I have something called increment. Increment, you just increment by 1. So let's just try to go through them, okay, because we don't have enough time. Let's see here how the syntax, how do I use this? Now add, we know all of us what's the meaning of addition. I'm adding this to this plus. So I have two opinions for this. I have destination and I have source. So when I say add D and add S, okay, D and S, they can be memory register sent to the move, memory register, register constant, yes. So similar to the move, you cannot use memory, you cannot use segment. So please be careful. So I'm adding S to D. So where do I save? I save it in the destination, which is this operand here. So if I have here AX, so I'm adding AX, DX to BX, I'm saving the result in AX. So this is your destination. This is where you save your result. You save it in the destination, okay? Then I may have carry. And did you study the status register in the theory? Did you study it? يا رب يكون طب الحمد لله. Finally. Okay. So you know that in the status register I have the flag bits. Like I have the carry flag bit, the parity flag bit, the auxiliary flag bit, the 0. So of course when I do addition, of course these bits are affected. And I can view them in my code. I can view them. I can see which flag is affected or not. So if I have carry from this addition, the carry will be saved in CF. CF equal 1, okay, there is a carry. CF equals 0, there is no carry. تمام? So this is for add. Now add with carry. If you notice here, I just add these two operands. In add with carry, no. I add the operands plus the carry bit. Okay? So that's why we call it add with carry. You add the source with the destination plus the carry. Now, of course, there are some flag bits will be affected, okay? The 0 flag bit, the parity bit, the carry flag, the overflow flag, especially if I'm doing signed numbers, the sign, right? So all these flags will be affected. So in this column here, it show you which flag will be affected when you are dealing with add. But let me ask you, what about move? What about move? Like, do I have carry flag? If the carry flag is affected? What about move instruction? Does this instruction affect the flag bits? Yes, yes, yeah, yes. Now for the increment, it's just add by 1. It will increment the register or the memory by 1. So it has only one operand. Notice here, in add, I have 2. Let me return this to S and D. Okay. In add, I have 2 operands. I need 2 numbers to add them. In add with carry, also I have 2 numbers plus the carry, add with carry. In increment, only one operand I have. Only one. That's why before we deal with the instruction, we have to understand how many inputs, and once we get the result, where to save the result. Where do I save the result? So increment, I have one operand and it will be saved in the same location. So see, it's adding the same operand plus 1 and saved in the same location. And of course, there are some flags will be affected. If the new value of D is 0, 0, 0, after adding, but the carry is 1, will the 0 flag or no? So it's 0, 0, and you add, and you got 0, and the carry flag 1. This is your question, right? Yes, it's still the flag bit 0, it will be 1. Yes, yeah. Yes. 0 flag indicate the value of the destination, not the carry. if you have 0 on the content or not, because carry will show me if I have carry or not. Okay, and here I show you the same, your limitation. I can use a register, memory register, okay? Now register immediate, right? The constant is the source. Yes, I can add this to this. Can I do this? Let me ask, add 1, 2, comma AX. Can I use this? Of course not, because I need a place to save, right? So you cannot do this. Memory immediate, yes, the source as a constant. Yes, I can do this. Accumulator, yes, I can do this. And I can use it with 8 bits size. I can use it with 16-bit size of register. This is for the increment. This is for add and add carry. This is for the increment. I can use it with 16 register size, 8 register size. I can use it with memory. Can I use it with constant? Can I say increment like increment 2 method, for example? So yes, we cannot do this because we need to save our result. Here I have example. Assume that AX equal 1100 and BX 0ABC. So what you do is just you're going to add this to this. And you have to check what are the flag bit that is affected. I know that we passed, it's 1047. And you have to leave. And I have a lab. So I'll stop here. I'll stop to slide 12. Because I don't want to take from your time. So in this example, it's just adding bx to ax. And of course, the result, it will be saved in ax. So c plus 0, I have c here. B plus 0, I have b here. A plus 1, it's b. That's why I'm showing b here. 0 plus 1 is 1. I'm showing here 1. So ax equal 1 bbch. It's, and you can check the flag bits. So I'll stop here, guys. You will come. In case you still have a question about the BB and SI, I'll just tell Dr. Ali if he will be with you, inshallah, on Thursday to answer this question. And also the limitation of the org. For you,